engine is not self-starting, so external power is required to crank it by rotating its crankshaft. In this video, we are going to learn about the starter motor, which is used to crank the engine. First of all, let's look at an outline of starter motor operation. The engine has a flywheel. The circumference of the flywheel is toothed, creating a ring gear. The pinion gear mounted to the starter motor meshes with the ring gear to turn the engine crankshaft, inducing the initial combustion. Let's look at the actual operation. There are three types of starter motor. This is a reduction-type starter motor whose operation we have just observed. This is a planetary type. And this is a conventional type. Now, let's look at the construction, operation, and inspection procedures for the conventional starter motor. The starter motor can be roughly divided into three mechanisms. An electric motor that generates torque, a transmission system that transmits the torque to the engine, and a magnetic switch that pushes the pinion gear so that it meshes with the ring gear while transmitting electricity to the electric motor. Now, let's look at the electric motor that generates torque. The outside yoke of the electric motor is made of steel and cylindrically shaped. Inside the yoke are field coils, made by winding coils around pole cores bolted to the yoke. The field coils are made of thick lead wire to handle strong electrical current. The field coils generate the magnetic field required to rotate the armature. One of the armature components is an armature core, which is grooved so that the armature coils can be wrapped around the armature core along the grooves. Both ends of each coil are connected to the commutator. The torque generated at each coil is combined to rotate the armature, that is, the armature shaft. This is the brush holder on the commutator side of the armature. Let's take a look at the brush holder from the commutator side. The brush holder holds 4 brushes, which are pressed against the commutator. Of the 4 brushes, 2 are supported by the insulated holders and are connected to the armature coils and field coils via the commutator. The other 2 brushes are grounded to the body. Next, we'll look at the starter motor transmission system. The transmission system transmits the torque generated by the electric motor to the flywheel. A pinion gear is mounted on the end of the armature shaft of the electric motor. When the magnetic switch is activated, the drive lever pushes the pinion gear to this position. At this point, the pinion gear meshes with the ring gear to crank the engine. When the engine starts, the starter clutch is activated, idling the pinion gear. Then, when the starter switch is turned off, the pinion gear is immediately disengaged from the ring gear. Let's look at the actual mechanism. The starter clutch is a one-way clutch combined with the pinion gear. There are screw splines inside the starter clutch. There are screw splines on the armature shaft as well, so that the pinion gear can move along the splines while rotating. The screw splines help the pinion and ring gears mesh smoothly. When the pinion and ring gears mesh, the engine is cranked. While the pinion gear is rotating the ring gear, the starter clutch is engaged. Once the engine has started, the pinion gear is rotated by the engine via the ring gear. The starter clutch is then released so that the pinion gear idles, preventing starter motor overrun. Let's move on to the third mechanism, namely the magnetic switch. The magnetic switch activates the drive lever to push the pinion gear, then leads electrical current to the motor circuit. This is a simplified illustration of the magnetic switch mechanism. There is a plunger at the center of the magnetic switch. The plunger has two functions: to activate the drive lever, which is attached to one end of the plunger, and to directly connect the main contacts via the contact plate attached to the other end of the plunger. The plunger is wrapped with a pull-in coil, which pulls the plunger to the main contacts. A hold-in coil is wrapped over the pull-in coil so that the plunger remains pulled. When the starter switch is turned on, electrical current flows to the pull-in and hold-in coils to generate magnetic fields. The magnetic fields then pull the plunger toward the right. This causes the contact plate to connect the main contacts. At this point, terminal 30, supplied with voltage by the battery, is directly connected to terminal C, which is connected to the motor. This allows strong current to flow to the starter motor. At the same time, the pinion gear is pushed via the drive lever to crank the engine with strong force. What is the construction of an actual magnetic switch? As you can see here, the pull-in and hold-in coils are fixed in the switch housing. The contact plate is located on the coil side with the main contacts on the opposite side. Let's also take a look at the magnetic switch with the housing disassembled. The pull-in and hold-in coils are wrapped around the plunger, which has a return spring like this. This spring returns the pinion gear to its original position after the engine starts. Here is a simplified illustration showing the integrated system of the three mechanisms we have observed, namely electric motor, transmission system, and magnetic switch. Let's look at the connections. The positive terminal of the battery is connected to terminal 30 and the ignition switch. Terminal C is connected to the field coils and armature coils grounded to the engine, and ultimately connected to the negative terminal of the battery. Thick cable is used for these connections to allow strong current to flow. Terminal 50 is connected to the positive terminal of the battery via the starter switch. Using this illustration, let's look at the operation of the starter motor from starter switch turn on to turn off. When the starter switch is turned on, electrical current flows to the pull-in and hold-in coils, then to the field coils and armature coils, and ultimately to ground. However, since the electrical resistance at the field and armature coils is very low while battery voltage is applied to the pull-in and hold-in coils, the magnetic fields generated by the coils pull the plunger toward the right. Via the drive lever, which is linked to the plunger. This movement causes the starter clutch to move toward the left along the screw splines of the armature while rotating. And when the pinion gear meshes completely with the ring gear, the main contacts are closed. When the main contacts are closed by the contact plate, the field and armature coils are connected directly with the battery. This causes stronger current to pass through the starter motor, rotating the armature with greater torque. Since the main contacts are closed at this time, the voltage levels at terminals C and 50 are equal, so the pull-in coil no longer pulls the plunger, which is therefore held in position only by the magnetic force exerted by the hold-in coil. When the starting switch is turned off after engine start, the main contacts remain closed, as shown here. Since electrical current flows to the pull-in coil from the main contacts, the coil generates a magnetic force opposite in direction to that generated by the hold-in coil. The magnetic fields generated by these two coils therefore cancel each other out. The plunger is then pulled backward by the return spring, opening the main contacts. At the same time, the pinion gear is disengaged from the ring gear and returned to its original position. The conventional starter motor incorporates an armature brake mechanism, which immediately stops the armature when the engine fails to start. This mechanism is constructed like this. Lock plates mounted at the end of the armature shaft support the brake springs. Let's see how the mechanism operates. While the starter motor is in operation, the entire armature is pushed slightly left by the drive lever. When the starter switch is turned off, the brake spring returns the entire armature to its original position. Since the armature is then pulled against the brake contact surface of the brush holders, it immediately stops turning. So far, we've observed a conventional type starter motor. However, reduction-type starter motors like this one have been used increasingly in recent years. Operation of the reduction-type starter motor is essentially the same as that of the conventional type. While looking at the actual operation of the reduction-type starter motor, we'll examine its construction features. When the starting switch is turned on, the magnetic fields generated by the pull-in and hold-in coils pull the plunger. This is the same as with the conventional type. Since the pinion gear is directly connected to the plunger, however, the plunger directly pushes the pinion gear toward the ring gear. When the pinion gear meshes completely with the ring gear, the main contacts are closed. At this point, the field and armature coils are directly connected to the battery, as in the conventional type. This connection allows strong electrical current to pass through the starter motor, causing the armature to rotate with great torque. The distinctive feature of the reduction-type starter motor is its use of a high-speed motor. The motor speed is then reduced by 3 gears to generate greater torque, which powerfully rotates the pinion gear. Next, we'll examine the planetary-type starter motor. Compared with the conventional and reduction types, this type of starter motor is more compact and lighter. The operation of the planetary-type starter motor is essentially the same as that of the conventional and reduction types. When the starting switch is turned on, the magnetic fields generated by the pull-in and hold-in coils pull the plunger. This is the same as with the conventional and reduction types. Also, the construction and operation of the pinion gear and starter clutch of the planetary type are the same as those of the conventional type. The distinctive feature of this type of starter motor is the mechanism that transmits the armature rotation to the pinion gear. The armature rotation is transmitted to the sun gear, planetary gears, and ultimately the pinion gear via the planetary gear shaft. At this point, rotation speed has been reduced to 1/5 the original level, while torque has been increased. This mechanism is also applied to automatic transmission vehicles. We'll begin the starter system inspection now. Let's start the on-vehicle inspection with the starter motor mounted to the engine. First, check whether the battery is operating normally. Check for faulty battery terminal contact and for disconnection of the battery cable core wire. In the example you see here, voltage reaching the starter motor from the battery is greatly diminished, even though the battery is normal. So the starter motor turns slowly, or does not turn at all. Now, using a voltmeter, measure voltage at various points during engine cranking. Before starting measurement, be sure to disconnect the center cord of the distributor so that the engine does not start. First, measure the voltage of the battery itself. The battery voltage should be 12 volts or higher when the ignition switch is off. Battery terminal voltage should be 9.6 volts or higher during engine cranking. Also, measure the voltage between the battery positive and negative terminals. It should be 9.6 volts or higher. Next, measure the voltage between terminal 30 and the starter body. Voltage that was 12 volts or higher before engine cranking should be 8 volts or higher during engine cranking. Then measure the voltage between the battery positive terminal and terminal 30, that is, voltage drop at the positive terminal cable. Voltage drop should be 0.8 volts or lower. Also, measure the voltage between the starter body and negative battery terminal to check voltage drop at the ground circuit. Voltage drop should be 0.8 volts or lower. Finally, check the ignition switch circuit. Turn the ignition switch to start and measure the voltage between starter terminal 50 and the starter body. Voltage should be 8 volts or higher. In some cases, amperage must also be measured during engine cranking. If the measured amperage is unusually high, check engine rotational resistance, which may be unusually great. This concludes the on-vehicle inspection for the starter system. Let's move on to the starter motor performance test. The simplest method of checking starter motor performance is the no-load test. A fully charged battery must be used for this test, just as for the on-vehicle test. Securely fix the starter motor, such as with a vise. Be sure to use a lead of sufficient thickness to accommodate strong current. Connect the battery positive terminal to the ammeter positive side and the ammeter negative side to terminal 30 of the magnetic switch. Connect the starter body to the battery negative terminal. Then apply the battery voltage to terminal 50. A voltage of 12 volts is thereby applied directly to the starter motor to conduct a no-load test. Complete the test as quickly as possible so as not to overheat the armature coils or the field coils. Be sure to take the ammeter reading when the indicator has stabilized. The specified current is 50 amperes or lower for the conventional type starter motor and 90 amperes or lower for the reduction and planetary types. Now, let's try a load test. The ammeter reads 40 amperes. Since this is a conventional starter motor, this reading is normal. We hope you have understood this load test procedure. Next, let's look at the magnetic switch performance test procedure. Disconnect the field coil lead from terminal C so that the motor does not rotate. Although the correct test method is to apply a voltage of 8 volts, you can use the simple method of directly applying battery voltage if it applied only for a very short time. Like the no-load test, complete the test as quickly as possible because the magnetic switch may overheat. Now, the pull-in test. Apply voltage to terminals 50 and C of the magnetic switch. If the pull-in coil operates normally, the pinion gear will move outward. Now we'll apply voltage. As you can see, the pinion gear moved outward. This is the pull-in test procedure. Next, the hold-in test. Follow the same procedure as for the pull-in test to pull the plunger. Disconnect terminal C and check that the plunger remains pulled. As you can see, it remained pulled. This proves that the hold-in coil is operating normally. Finally, let's look at the no-load test procedure for the reduction-type starter motor. The connection procedure is the same as for the conventional type. Apply the battery voltage directly and complete the test as quickly as possible. Before starting the test, confirm the location of terminals 30 and 50 on the reduction starter motor. The procedures for both load and no-load tests for the planetary type starter motor are essentially the same as for the conventional and reduction types. The starter motor's function is to induce initial engine combustion. The driving force for this function is the battery. The starter motor does not operate if the battery does not supply sufficient voltage to crank the engine. The starter motor consists of 3 mechanisms: electric motor, power transmission mechanism, and magnetic switch. In this video, we've shown the construction, operation, and inspection procedures for these mechanisms. Be sure to strengthen your understanding of what you have learned about the starting system in this video by studying the relevant training manual.